So this is a talk, Stream All the Things. The photographs are pictures of water, and they're all ones I took. But since we're talking about streaming, I thought, why don't we overload the word even more? As you may know, I work for Lightbend. My name's Dean Wampler, and I run the team that's developed our fast data platform that we're actually releasing next week after all this time. And this isn't a talk to promote it so much, except just to talk about the kind of decisions we made about streaming engines, about the architectures you have to build to deal with streaming. And if you come from a data world where you're used to things like Hadoop, what has suddenly changed in your world if you want to do streaming? So that's kind of the purpose of this talk. This is actually in Glacier National Park. I forget the name of the lake now, but anyway. There was a booklet in the handout that kind of goes into a lot more detail than obviously I can cover in an hour, and you can get a PDF version if you want to go to this link. But let's start by putting streaming in context. Why did we get here in the first place, and what were we moving from? Well, I think the answer's sort of obvious, actually. We had really been kind of focused on sort of batch mode architectures, and Hadoop is sort of the canonical example. In a Hadoop architecture, you basically have something that looks sort of like this, and there are really three sort of main components that you need. One is some sort of storage, and in the Hadoop case, the default storage is the Hadoop distributed file system, which is, it gives you the illusion that you have one big file, or file system, but it's actually distributed over a cluster. It's not even a very good illusion because it's not even a POSIX compliant file system by default. It's actually kind of annoying to work with, in my humble opinion. But there it is. And then, so you've parked all this data, so what are you going to do with it? Well, you need tools that you can write jobs that can process the data, so that's where tools like originally MapReduce and now more recently Spark emerged as tools to write this stuff. And when you actually submit your job, there's this thing called Yarn, yet another resource negotiator that figures out how to take your job, take what you've said as the data sources you want to process, and then break it up into tasks across a cluster. Pretty standard stuff in a lot of ways, and not going away by any means, but nevertheless sort of a canonical way of thinking about this problem. And notice what we've actually done here. We've sort of turned the database inside out. It used to be the database was this opaque thing. You really didn't have any idea how it was storing data and how it was taking your queries and processing them. Now we've broken it up into separate storage, separate compute, and so forth, which is both good and bad. It's greater flexibility, but it's also a lot more hassle because there's plenty more things to go wrong if you're kind of stuck with the management of this stuff yourself. And just for completeness, I also added tools and examples of data that you have to get into the system, or in some cases, get out of the system. But again, it really is, again, oriented towards, I'm going to just ingest all this stuff and then go back and process it later, where later could be a few minutes, it could be a few hours, it might even be days, or if I'm looking at what happened last year, I might be running these massive jobs on January 2nd or something while I'm still trying to sober up. But it wasn't really designed originally for processing streaming data and giving me quick answers as soon as data arrived. But it was really good at low-cost batch processing. Those of you that work in the data world have probably seen numbers about comparing a Hadoop cluster total cost of ownership to like a data warehouse appliance, and it's dramatically cheaper, even orders of magnitude. Nicely supports multi-users, diverse workloads and all that. When I was doing Hadoop consulting a few years ago, a lot of the work I did was actually just replacing data warehouses with Hadoop. But the old saying is time equals money, right? So my favorite example of this actually of something that used to work just fine as a batch mode approach, but actually is a competitive advantage when you do it in streaming is search engines. So if you think about what Google did in the late 90s when they got started, like everybody, they would have web crawlers constantly walking the web, and they would collect, here's the URL and here's the data or web page, whatever, at that URL, and then periodically they'd run batch jobs to sweep through that and update their search index. And that had worked really well for them. I think they did okay with that approach. But now you think about it, what happens today, you hear about, a fire in California or, a political unrest in Europe or something, and you immediately, type in a search query because you want to get the, most recent up-to-date news. Well, that's not so great if Google is still like, it's going to be an hour before the next search index happens. Meanwhile, CNN or whatever has already updated their site with information. So even something that used to work fine as a batch process, actually it's a competitive advantage if you can convert it to a stream process because you're shortening that time between data arrival and value extraction. So we get more complicated architectures as a result. Now the numbers correspond to the diagram that's in the book, where I, just to make it easier to reference the text and the diagram, so you can ignore those. But I will walk through what I'm going to do is I'll walk through the whole architecture and talk about the role of each piece, and then we'll mostly focus on the streaming engine part and how they play out. So the first thing I have is data coming in, right? And I basically broke it up into three kinds of data. One would be like the REST requests that we're all used to using, whether they're blocking or not, for like web sessions or calling for service from another web service. There's this thing called microservices that some of you may have heard of that are used for this sometimes. But it's not usually the sort of vehicle you think of for like a massive ingest of some huge stream of data like the Twitter fire hose or something. And for that I use the word sockets to indicate like this, really to kind of be a placeholder for this external data that's coming in, and it's going to be get it or lose it. I can't go back and ask Twitter for the last hour of data again if I happen to have lost it. And then I use logs to maybe represent everything that's internal. It could be server exhaust logs of metrics that I want to analyze, or it could be domain-specific logs like click streams that I want to analyze for usability studies. I actually worked on a project. I worked for a finance company in Chicago a number of years ago, and we actually wrote this system that would capture all of the IP traffic coming from the exchanges, and we actually used it for basically not logging, but sort of like accounting regulations and just making sure that we actually captured every trade properly by looking at it at the IP traffic level. It was kind of crazy. But nevertheless, logs like that can be used for domains problems as well as just like server analysis. Well, if you're doing REST input, a lot of what is emerging in these architectures is, I actually need microservices in the middle of my data environment because I not only have to process requests for service from outside or even internal, but I have also got to be able to provide easy access to my domain logic, like the regulatory rules that I have to follow, or if I'm doing accounting software, maybe the tax rules or something like that. And the correlation that we're seeing is that a lot of these even stream pipelines that you would think are just kind of like batch pipelines, only faster, actually have to look a lot more like microservices now. And the reason is, if I write a big batch job that sweeps over terabytes of data, but it's just maybe at 12:01 I start this job that looks like 12:01 a.m. that is, that it's going to look at yesterday's activity and do like the accounting for whatever my e-commerce site was doing yesterday. That's probably going to be done in a few hours at worst. But if I start a streaming job that's like updating my search index, I may never turn that off, or I might roll up versions every now and then. But this thing is going to run for a lot longer. And as we all know, if you let something run long enough, you will run into every possible weird, oddball scenario that could possibly happen. Network partitions, hardware failures, spikes and troughs of traffic. And so suddenly they have to be reactive, these data pipelines, whereas maybe that wasn't such an important thing when I was just writing batch jobs. So the microservices story is not only here because I do need to write microservices to provide everything else that I don't get with Spark or whatever, but it's also because now my streaming jobs are starting to look like microservice jobs more than they used to. I have Zookeeper here because a lot of tools like Kafka use Zookeeper for master federation and stuff like that. Zookeeper is really the data backplane. How many of you ever worked with enterprise service buses and are willing to admit it? I saw some hands go, I'm not sure. Well, most of the ideas in industry, we usually come up with a pretty good idea, then we completely screw up the implementation, and then somebody comes along later and actually invents a good version of it. And to me, Kafka is kind of like this. It's really ESBs done right. It's really a great data backplane for a lot of reasons. And well, one of them is just the fact that I can actually rationalize my architecture. So I deliberately drew this as bad as possible, not because I suck as an artist, but just to make it as messy as possible. But here I'm pretending that I've got a totally bipartite graph with a bunch of services on the left, and they're talking to everything on the right. So what happens if I lose one of the links from, let's say, the internet bubble to service 2? Well, then I potentially have data loss. And until something comes up again to replace service 2, I could be losing that Twitter fire hose or whatever. So one of the values of Kafka is that we solve all problems in computer science with another level of indirection, right? So here we are. So what we're doing is, if service 2 goes down, then hopefully I'm capturing the data from the internet reliably in Kafka, and I can take my sweet time getting service 2 back up. Well, until I run out of disk space at Kafka, but I have that that sort of buffer. The interesting thing about this too is it sort of also kind of partially solves the problem that we use back pressure for in like reactive streams. If you consider a disk to be infinite resources, you actually have an infinite queue. We don't necessarily need to go into that as a debate, but that is one of the things that some of the people that are real Kafka partisans argue. Now, there's a couple of other benefits here. So I can have arbitrary numbers of producers and arbitrary numbers of consumers on either end. The other thing about Kafka that's a little different than traditional message queues is kind of an important technical distinction. Most message queues are designed such that when I read a message from the queue, it actually consumes it. And it actually makes the queue design very simple. The disadvantage is if I actually want to have several different types of consumers all see the entire traffic flow, then I have to do something else to make that data available to everybody. In Kafka, they manage the life cycle of each event internally, and so I could have my dashboards and my usability studies and my machine learning models and my mainline data flow all looking at the same Kafka topics, which they're a term for a queue, and they'll see everything. And I don't have to worry about multiplexing or anything like that. Kafka kind of manages all that for me. So it's a really nice tool for these data backplanes, ESBs done right, and so forth. I'll come back and go into details about these various streaming engines that we have in this diagram, but first let me finish the rest of the diagram. Obviously, there's all kinds of storage you might need, everything from distributed file systems like HDFS, object stores on the internet like S3, search appliances, databases, and so forth. And then this architecture is not really specific to any kind of infrastructure, so you can run this in Hadoop Yarn. We don't actually think it's a good idea to do it there, but we're biased. We actually like Mesos for this. And I'd be happy to talk to you in our vendor area about why we pick Mesos without going into too much detail now. But you can also run it in cloud environments. So let me go back and discuss the streaming engines in a little more detail. And so basically, in the Fast Data platform, we decided to put in 4 streaming engines. And I was very concerned about the paradox of choice. Have you ever been in this situation where you've walked into like Best Buy and you went in to buy a new refrigerator and you look down this long line of refrigerators and you panic because you don't want to buy the wrong one, so you end up walking out. That's the paradox of choice. So the reason we picked 4 is we felt like if you consider all the possible things that you might have to do with a streaming engine, we kind of felt like you needed 4 choices, even though they overlap to some degree. And I'll try to explain what each of them brings to the table, as well as the kind of considerations that went into it. So if you were about to build an application and you needed to decide, which streaming engine should I pick to process this data, here's some characteristics you'd want to evaluate. The first one is, what's my latency budget? How low does it have to be in order for me to get, to take that input data and do some processing? And there's several levels where this could go. We're not really talking that much, at least in this venue about like picoseconds to microseconds, the sort of true real time that they use for like rocketry and even self-driving cars to some degree. Obviously, when you're at this level, you're not using Java, you're not using the JVM, you're not using clusters, you're using like custom silicon and network cards that bypass the kernel and crazy stuff like that. And even when you get up to, well, actually, this is really with the previous slide. So if you work in finance, you're probably all these buzzwords mean something to you probably. But when you go up to, let's say, under 100 microseconds, then you have a little bit more flexibility. So this would be more like what normal trading as opposed to high-frequency trading looks like, or ultrasound machines. I've got images, I'm scanning babies or whatever, and I want to do something with that data. And it turns out this is the realm where the JVM can work if you know what you're doing. So there's some very low latency oriented systems like Akka actors, and there's something called the LMAX disruptor that some of you may have heard of that came out of the London finance industry. Very high throughput, low latency message queue. When you get down to the 10 milliseconds, then that opens up even more options. Now, so this is not a picture of water. You might ask, why are there credit cards here? Well, I had this conversation with somebody at, I think it was Deutsche Bank or something once, who we were talking about authorizing credit cards, basically. And he said, if you think about, like you click buy on a website, and the usual rule of thumb is that you're supposed to get an answer back in like 200 milliseconds, otherwise you start to get distracted or whatever. That's kind of the usability rule of thumb. He said, we get 10 milliseconds. All the stuff that has to happen in that chain, we only get 10 milliseconds to decide whether to authorize this card or not. So that's like their latency budget for that. Which is why they just say no for me all the time. I'm not sure. I guess that's what, they just have a hard-coded rule. Just no. No! And now when you get into this 10 millisecond range, then some of the big data tools like Flink that were really designed for low latency can actually be used if it's really a big volume. But this is a sweet spot for Akka, for Kafka streams and tools like that. When you get up into the hundreds of milliseconds, and this might be the place where I'm going to do some scoring with machine learning, but I don't necessarily have to do it in very low latency. And that's why this picture of this robot-like thing is there. It's actually the icon from a Coursera course. At this level, okay, well, now we can maybe think about doing little micro batches. Instead of looking at each event one at a time, I can actually get economies of scale if I process little batches at a time. I just run little jobs. I'll accumulate the data, run a job while the next batch is accumulating and so forth. This is, in fact, how Spark is implemented to do streaming. At least as of today, they're trying to get rid of this model because it is a bit of a, it limits them to a few hundred milliseconds. But it is one way to do it. Especially, you have to do batching like this if you want to do like joins in SQL. You really don't want to do like per event joins if you can avoid it. And if you get up to like seconds to minutes, this is where you get into things like I want to incrementally train my machine learning models, but I don't need to have like the model that's up to date to the millisecond. It's okay if it's a few minutes, even up to hours out of date. Or I'm doing ETL, where I'm just ingesting the fire hose of data from my partners. I don't necessarily need it in real time, but I do need to clean it up, route it to the right place and get it into the final storage for internal consumption. And when you start getting into minutes, then I really think, for reasons I said a minute ago, you should just run batch jobs. You don't want to keep something running that has to be resilient, scalable, distributed, and all that stuff for years when you can just kick off a batch job every 5 minutes or whatever, and then it just has to be right-sized, if I can use that horrible word, for that few minutes it's going to run, and then it just goes away, and the next job will be different. All right, well, I spent a lot of time talking about latency. The next question would be, what about volume? How do we do it? Volume. Something. Anyway, so what is your volume budget? So if you're under, say, and these are all approximate numbers, right? If you're under, say, tens of thousands of events per second, most really good REST systems will do this for you. You can easily scale for that kind of load. If you get, let's say 100,000 or so, then you really need to be using non-blocking REST, or you're going to have a lot of inefficiencies in your system, like the actor library, which is great for this. But you can still reasonably process things individually. You don't necessarily have to go to bulk processing. When you start to get into millions of events per second, then you get to the point where it would really be good if I can just take this input fire hose and immediately partition it so that I'm running in parallel over a cluster. The reason I have a Nest thermostat on this picture is an interesting war story I was told by a Nest engineer once. Turns out most people get up at about the same time every day. So they would get these huge spikes of traffic, in every time zone, like 6 to 7 every morning, when all of these thermostats suddenly went into, like daylight mode. And they had to do all kinds of stuff to kind of jitter to basically, spread that out and balance it. But, they were literally dealing with, very large swings in traffic every day as these thermostats phoned home. The next kind of question would be, all right, what kind of data processing have I got to do here? Am I actually doing SQL? So one of my colleagues, Boris Lublinsky, went to the Flink Forward conference in Berlin recently, and Alibaba, who's maybe the world's biggest Flink user, if it's not them, it's Uber, said that Flink now has a SQL API, and it's really like a scripting language on top of their streaming engine. You've tried to put that together. SQL and scripting, yeah. But they're actually converting all of their Flink jobs to use the SQL API. And if you think about it, if those of you that know the Scala collections library, you have things like map, which is really like a select statement, and filter, which is like a where clause. So a lot of the things that we're used to in these Java Scala libraries actually have direct analogs in SQL, and SQL is often the most concise way to write these things. So as long as you have a mechanism for plugging in user-defined functions so that you can call to your machine learning models, or you can do whatever weird, regulatory calculation you have to do, why not just write it as SQL? And so that is actually, SQL is one of those things that never dies. As many times as you try to stab it in the heart, it just won't seem to go away. It keeps coming back. Now, maybe this is a bit of a fad right now. Kafka recently introduced a SQL dialect for Kafka streams, but it is, it's taken seriously because it requires relatively less technical expertise to use it on the part of the end user who's writing these analytics jobs, and it's very concise. So actually, the example here is the Spark sort of analog API that's basically writing a SQL query in Spark. And you could literally write this as a SQL query with a string if you wanted to, and we all know that stringly typed code is the best code, right? Are you doing basic ETL? One of my favorite examples of Kafka streams actually is, I've got these raw log messages coming in. They're just text, but that really sucks to work with just strings. So I'm going to have a Kafka streams job that reads that topic, parses each of those into a record format, and then writes to a new topic so downstream consumers have some nicely formatted schema to work with. Not the only use for Kafka streams, but it's a good one for this purpose. Am I integrating machine learning where I need to train models and serve them? That is actually a non-trivial problem in this space. Like maybe I want to use that mini batch model of Spark to periodically update my models, but then I want to actually use Akka to score events as they come through. So how am I going to get those models from Spark over to Akka? This is actually a problem we've been thinking a lot about. I mentioned Boris, my colleague. He's actually going to do one of those little thin O'Reilly booklets any time now that actually focuses on model serving. So keep an eye out for that one. And then this other interesting question of, do I really need to do complex event processing where I really need to look at each individual event? It has its own identity, its own meaning. Maybe this guy is indicative of an error and I need to send off an alert, or this one is triggering some other action in the system. Or are they kind of anonymous in the sense that they're all records and I can kind of treat them all together as in bulk, the way you would think of like a SQL query? Where you don't really, you can certainly do SQL where you ask for it, give me the record for this person with this ID and then do this to it, but more about what's the bulk processing I might do. The reason I bring this up is it turns out tools like Akka are really great at those single event processing, whereas tools like Spark and Flink are really great for that bulk processing. And sometimes you need to think about this just in terms of amortizing the workload that you're trying to do if you have a lot of data. And the last one is, how do I actually want to deploy this and run it? This is important because some of these streaming engines are actually libraries you embed in your app, and then you have to figure out how to run them, how to distribute them, and so forth. So that with great flexibility comes great responsibility, I guess, or something, because now you have to figure all that out. But you have that flexibility. Whereas others are actually, you're running this system like Spark and Flink, and you're submitting stuff to it that's a little more than like a script, like a SQL statement, and then it figures out how to partition and distribute and all that stuff. So that sort of application deployment and structuring is important. I guess actually there's one more, and that's what do I need to hook this up to? So it turns out Kafka Streams, for example, really is only designed to read and write Kafka topics. But what if I want to ingest like a REST point, or I want to talk to a database or whatever? I've actually mentioned all the engines I'm going to talk about in passing, but now just to dive into them a little bit. The four that we decided to pick are Flink, Akka Streams, Kafka Streams, and Spark. And the reason is not that there aren't other good options, but these all have vibrant communities. They cover the spectrum of problems that I mentioned. And we felt that by supporting four of them, although I wouldn't recommend that everybody use all four, that you can kind of do anything you need to do. And there's actually a fifth one here, which is the one that's kind of sideways, and that's Beam. So let me talk about those, and I'll start with Beam. So Beam is actually the small talk of the big data world. And what I mean by that is, how many of you actually ever wrote small talk code? A few of you. How many of you actually know what small talk is? All right, point taken. So it's one of those systems that was incredibly influential, but nobody used it, right? So I kind of think Beam might fit into this category. It's actually driving the innovations in all these other projects, but there aren't that many people actually using Beam itself. So what is it? So Google has been thinking about stream processing for a while, as you might guess, and they've gone through several iterations of thinking about how to write a stream processor. And the latest is called data flow. And a few years ago, Google decided, you know what, instead of just writing research papers about our stuff, why don't we just actually open source the stuff so people actually use it instead of some knockoff imitation. And what they did with Dataflow, instead of open sourcing the whole thing, they open sourced the top part, which is the thing you use to define your data flows that has the semantics about all the weird things that you might want to do. And then you provide a runner, if you're not running Google Cloud where you can use the whole thing, you provide a runner. And it turns out tools like Flink are the most mature options for being a runner. So Beam is really great for thinking about what are the kind of sophistication I might need in my stream processing, but I'm going to have to run it on something else if I'm not running in Google Cloud. And just to give you just a taste of the stuff that they have been thinking about, and actually I think the URL, that's something else. Anyway, if you get these slides, I actually always put my footnotes in the slide deck, and I actually have links to the presentations that I think everybody who's doing streaming should look at from the Google team, because they really go into great depth about all these semantics I'm going to describe. And one of them is actually writing a book for O'Reilly that's coming out this fall. His name is Tyler Akadow, if I pronounced it correctly. But just to give you an example, suppose that I was actually going to use streaming to process my data from my accounting system. In other words, I need it to be right. And let's suppose, for the sake of argument, that every minute I need to know how many SKUs did I sell in my different stores around the country, Walmart or something. And I actually needed this for accounting purposes. I immediately run into the time of flight problem that Jonas mentioned last night, where even in a perfect network, it's going to take time for all the events to arrive at my analysis cluster. And if things go really bad, like I have a network partition, it could be hours. So what I'm showing here is these events from different services that are sending information that I need for this analysis to my analysis server. But even though I have these window boundaries of minutes, some of the data is going to be late. So what do I do with this Do I decide I'm going to wait 5 minutes and then just do an approximate calculation with maybe the ability to correct it later if I actually get late arriving data? Or am I just going to do an approximate thing where I don't care about accuracy? These are the kind of problems you get into when you want to push the envelope of accuracy while at the same time accounting for the realities of stream processing. And that's what Beam has been working on a lot. So it's been very influential for environments like Flink and Spark and others. So Flink is sort of analogous to Spark if you haven't used it, in the sense that it is designed for high volume, where it automatically partitions your data as needed over the cluster. But it was implemented originally as a low latency system, not a batch system, rather a streaming system, not a batch system. So it does do low latency very well. It is the most mature Beam runner. One of the systems I'm not going to talk about is Apache Apex, and they also have a fairly mature Beam runner if you're interested. And they have a new and very rapidly evolving SQL abstraction as well as the machine learning libraries. I probably should have changed the order a little bit and talked about Spark. In fact, I'm going to do that. I'm just going to talk about Spark next, and then I'll come back to Akka. And the reason I'm doing this is because Spark, like Flink, runs as services in your environment, and you submit work to them, and they figure out how to break it up. So Spark originally was a batch system, and they came up with the world's biggest hack. What if we just run mini batches and call it a streaming system? We can't do real streaming, so let's just call it let's just do mini batches. So this is going away. The so-called structured streaming that is now in the most recent version of Spark is getting close to production ready, and it will largely eliminate this mini batch model. But if you're working with the older streaming engine, you basically say, I want to run with these windows, or actually they're durations. Windowing is another term, down to maybe half a second. And then every half second, I want you to run this job over the data that you've captured. And then Spark figures out how to capture the data and process it and all that. But it does have a really rich SQL dialect that's like ANSI 2002 compliant. It's probably the most advanced of all the streaming engines, and a growing machine learning library. And so true streaming will be coming, as well as actually being able to run Beam jobs is coming as well. Now, the nice thing about Spark, though, is if you are running Spark, then you can also run batch jobs, so you can actually do the Lambda architecture, if you like, where you actually have logic written once, and then you can run it in your streaming pipeline and also your batch pipeline. This is actually the biggest problem with the Lambda architecture, is you ended up implementing everything twice, once in your batch mode and once in your streaming mode. Let me go back now to Akka streams and Kafka streams. Here we go. So Akka streams and Kafka streams, instead of being services you run, although there are some services you can run that are kind of support services, they're really libraries you embed in your application. So they fit more of a microservice model where I need to do event or stream processing. Excuse me. I get all choked up when I talk about Akka streams. Okay. Most of you may have used Akka if you're at this conference, but it is really great for very low latency. And here it's actually low latency but efficient per event processing, as opposed to being efficient when you aggregate over a large chunk of stuff. So you would not use Spark, for example, to do processing of a low volume stream, because you're just going to carry a lot of overhead. But if you have a relatively low volume stream up to anything that fits into a single JVM, then Akka streams will be very efficient for it. It has in particular, the streaming dialect on top of the actors has a very rich graph model. You can do things that I've seen nobody else do, like feedback loops, which it actually would be interesting if you wanted to implement neural networks in Akka streams. That would be the only way to do it compared to Kafka streams or whatever is with feedback loops. But also it gives you a lot of flexible capabilities for interoperating with other systems, including your microservices that are serving web requests, writing to databases and so forth, and persisting state in your streams. Kafka Streams is, I think, a good example of a library that doesn't try to be all things to all people. It just focuses on some common problems, and then you have to do something else. So, for example, like I said earlier, it doesn't try to talk to the rest of the world, it just talks to Kafka. but they do have some really great abstractions in it for doing things like ETL, like that example I mentioned earlier of log processing, where I have single records and I'm just going to read each one of them and then process them in some way and write them back to Kafka. But they also have some nice table abstractions, like if I just want to see averages, or I just want to see the last value for a given key, but not the entire history. You know, if you may have heard this expression that tables and streams are dual to each other. You know, streams are like a snapshot, or rather, tables are a snapshot in time, and streams are like the whole history. So Kafka Streams has a lot of nice libraries for this. This is actually that example, again, I mentioned earlier of parsing logs. And they recently introduced this exactly once idea in Kafka Streams. I put it in quotes because if you talk to a theoretician, they'll tell you that exactly once is impossible. But if you like set your boundaries, you can effectively get exactly once. So, and all that really means is they're doing at least once, but then they handle deduplication for you. So it's effectively like you see once and only once records. We talked about Spark streaming, so I'll skip past this. And I'll skip past this slide on the Lambda architecture. But let's talk a little bit about microservices again and how they fit into all of this. This rock, it looked like a sliced beef kind of thing. It's in a lake in the Ansel Adams Wilderness outside Yosemite. So the question I want to ask here is, how does something like this is that architecture diagram again for stream processing, how is that like, say, what you might think of as a classic microservice architecture? And here I just made up a diagram with some set of services that are autonomous that do things like order processing, account management, and so forth, each with their own database, sending messages to each other for other services, right? I actually think that they're a lot more alike than different, even though superficially they look different. And here's some of the reasons. If you think about the kind of Spark jobs you write, they tend to be single responsibility. Like, I'm going to do payroll for last week, or I'm going to analyze what happened in my stores yesterday. So you're writing all these little jobs. They tend to be very small. And even though the services underneath may not quite look like what we think of as microservices, your jobs do have that kind of quality of being single responsibility, just as microservices are supposed to be single responsibility. And of course, that's important because then you can scale them independently, you can replace them with new versions without affecting others and so forth. So you get all those kind of benefits. Both microservices and stream processing, they're dealing with input that's never going to end unless you go out of business, which is a scenario we don't want to think about. And that means that both have to be, available to respond to, whatever it is that's coming in. They have to be resilient against failures, including bugs in their own code. They have to be scalable and hopefully dynamically scalable and all that. In other words, they have to be reactive. And I think going the other way, actually, to kind of force fit this story to work better, if you start out building microservices, you eventually, if you're successful, are going to find that data becomes an increasingly dominant concern. And my favorite example is Twitter. Those of you that have been on Twitter a long time, like I have, know that originally it was like a Ruby on Rails app, 3-tier app, which is why we saw so many fail whales. And apparently the big reason was the so-called Justin Bieber problem. So Justin Bieber was the first guy that had over 1 million followers. And the problem was whenever he tweeted something, they suddenly had to send millions of notifications to all of his fans. I know many of you here are Justin Bieber followers, so you know exactly what I'm talking about, right? And so they had to change their infrastructure, and today their infrastructure looks like giant pipes. They've just got these massive pipes of data flowing through. They actually still have Ruby on Rails in there for like the UI, but most of those pieces have been pulled off into microservices that are micro in the sense of being single responsibility, but are actually really massive pipes of stuff. So my argument is that in the recent past, we tended to think of services kind of in one bubble, and in the sense of, what are the things that keep me up at night if I'm an engineer writing services. But if I was a big data guy working in Hadoop, I had other things that I worried about. And they overlapped a little bit, as they always do, but there wasn't a lot of overlap. Whereas I'm arguing that today, the people who are writing streaming data services have to really know and do the same things that people who've been writing services are writing. And just 2 architecture slides. So what we tried to do was take what we learned about stream processing and building microservices and put it into a platform that does a lot of the hard work for you about providing a supported experience, an integrated experience, best of breed, open source tools, and then all the management stuff you need. And that's what this is, our fast data platform. And you can tell this is a commercial product because this diagram's in color. But really, all the things circled in red are the things we talked about. Actually, it's a little off in one spot there, but we'll not worry about that. And then, of course, we added the usual commercial stuff you need, like management and monitoring. And I'd be happy to demonstrate this stuff in our booth to anybody that wants to see it later. And then, actually, we decided to use Mesos. So I just briefly, why Mesos versus Yarn? I alluded to our choice for this earlier. And the reason is that we wanted a system that kind of had learned the lessons of early tools like Yarn, but was actually designed to run your entire ecosystem and not just a subset of it. Like Yarn actually can only run Spark and like MapReduce kind of jobs. You don't actually use Yarn to run HDFS or HBase or those things. You statically wire those yourself. But if you have a massive cluster of thousands of nodes, it'd be much nicer if your cluster infrastructure could just run everything that you want to run. And that's why we like it. Okay, so to wrap up a little bit with a sunset picture, this is Olympic National Park. The easiest backpacking trip I ever did, because literally it was like 100 feet elevation at most through the whole hike. Anyway, outside Washington. I encourage you to read this to get more details than I have time to cover here. I think we also handed out this book from Jonas that covers microservices. But yeah, come visit us in the booth. And I'll post the updated version of this presentation on my website, which is in the notes, which means you don't know where it is. It's a polyglot program. Actually, do I have it on there? I guess I do. Yeah, that polyglotprogramming.com is where I put my slides, but this will be on the conference site as well. And if you want to learn more about the fast data platform and you don't have time to talk to us or don't want to talk to us, you can go to this link and find out more. Okay, any questions? Over there.
Just quickly, I was going to ask, in terms of the very last point that you were talking about Mesos versus Yarn, if you're setting up an environment and you've got any actors that you're creating, any microservices, are you, if you were choosing Yarn, wouldn't you be stuck, as you said, having both Yarn and then some other management that might end up being, Mesos or something related to that, just to manage the environment for the other resources?
Yeah, I think you would. And I think what people are doing in the Hadoop world, some of the vendors are starting to talk about Kubernetes as an alternative. And it turns out Mesosphere is also adopting Kubernetes as a second option on top of Marathon, which is sort of an analog, roughly speaking. So I think what we're going to see with microservices is most people will standardize on Kubernetes because that's kind of what all the cool kids are doing. But they'll run it on top of these more mature systems like Mesos and Yarn to try as best as possible to interoperate with things that don't know Kubernetes yet. And that's certainly kind of the way we're thinking about this problem right now. There's a couple over here.
So you brought up, you brought up complex event processing. I was wondering if you could speak a little bit more, because most of what I see are systems geared more towards ETL and less towards CEP. So.
Yeah, complex event processing is a pretty interesting thing that certainly isn't going away. And especially, we're trying to think about what would a big heterogeneous system look like where I have to do everything. It turns out Flink has a nice library for this for like large scale, but it's something that people have been using Akka to do for a long, long time. So You could even use Kafka streams for this. The problem is that all you can do is write back to Kafka topics. Well, you can't, I mean, once you're in code, you can do anything you want, right? You could certainly call a database or something, but I do like the connectivity libraries that have emerged in the Akka community. There's this Alpaca project, A-L-P-A-K-K-A. Anyway, that I think would be great if I wanted to send notifications to some service, write to a database or whatever. So I think all the pieces are here. And also all the pieces are here to still do batch because you've got HDFS and Spark and all that. So, yeah.
You spoke about the kind of convergence of microservices and maybe big data processing. How do you see like serverless architectures kind of playing into that mix as well?
Yeah, serverless is really an interesting story. It's interesting both, like the cloud vendors have figured out that they need to lower the cost that you pay, so they're using that as a way to cut down the delta of time that they charge you for. One of the things we're actually looking at, IBM open sourced something called OpenWhisk, which is like a serverless framework that's built on Akka. And I think that's going to be an interesting way to solve a general problem that isn't just specific to serverless, but is I want to absolutely reduce to the bare minimum what somebody has to do to get their job done. So if I can offload everything about running something, even if it's in my environment, but I have a team that provides the serverless infrastructure, or they're the ones that provide the Spark infrastructure for the data scientists, then all those people have to worry about is that little bit of logic they need. So we haven't really added anything specific to serverless in this platform. It's, like I said, it's going GA next week, so it's not that mature yet. But it's certainly something we're thinking about, both just in a larger context of our microservice story. Why would you do anything else, really? Well, there is a reason, and that is you are losing some control over your latency and those kind of things. So you always have to figure out, there's never a free lunch, right? You have to figure out what the trade-offs are. But for a lot of cases, it would be the natural thing to do. Is there anybody else?
Hey, I had a question. For the fast data platform, what about the authentication, like support for Kerberos?
Yeah, so that's an interesting one. One of the reasons we actually picked Mesosphere DCOS over Bare Mesos is they gave us a lot of the enterprise capabilities, like Kerberos integration that you need. I have to say, to be honest, it's an evolving story. This is always an area where the mature established vendors or players like the Hadoop ecosystem are much more mature than our ecosystem. But that's the kind of stuff that we're working on real soon now, I guess is the way I'd put it. But that would be the first one we finish working on with Mesosphere is Kerberos integration, like controlling my HDFS with Kerberos and having Spark do the right thing to send the tokens over and so forth. But it's not quite done yet. Maybe one more? Maybe way in the back there.
You mentioned the higher overlap between microservices and fast data. Can you elaborate a little bit on that?
Right. So what I think is we're going to see is I see it happening in a couple ways. One is that even your data processing, your stream processing stack will be designed more like a microservice so that it has the kind of resiliency you need over its long life cycle. The whole reactive principles, scalability, resiliency, failure handling and all that. But the other part being that your ecosystem, your architecture will look less like these big systems that are just running these massive jobs and more like lots of small heterogeneous tasks or processes running that communicate through some appropriate means, where that means could be REST if it's sufficient enough for your problem. If it's not, it might be asynchronous socket connections and stuff like that. So I just think that there's a whole lot of converging factors that are making both the architecture look more like just all microservices, even when I'm running things like Spark and so forth, but also just the need from a business sense of now I need to provide better integration with all these tools because it's not like in a sort of stereotypical Hadoop case where I just have all the data parked in HDFS. Now I'm going to run some big thing that's going to do the roll-ups for yesterday. Now I have this stream of data, and it needs services from other providers, like for doing reference data handling and stuff like that. Okay, thank you very much.